Hello and welcome back to Functional Analysis. And as always, many thanks to all the nice people that support this channel on Steady or PayPal. This is part 26 and I still want to show you more main results in the topic of functional analysis. Today we will talk about the so-called open-mapping-theorem, also known as the Banach-Schauder theorem. As the name suggests, the theorem is about open maps. Therefore, I first want to start explaining what an open map is. The notion openness we define for metric spaces, so therefore let's choose two metric spaces X and Y. Of course, now we want to consider a map from X to Y. Now such a map F gets the name open if it sends open sets in X to open sets in Y. In other words, if we take any open set A in X, then the image f of A should also be an open set. However, please don't forget, the notion openness is always given with respect to the corresponding metric space. Okay, so this looks like a natural notion, therefore let's immediately look at some examples. First, a very general example, because you might already recognize the connection to the definition of continuity here. So let's fix a bijective map, which means we have an inverse map f to the power minus 1. Of course, this one now goes from y to x, and we also choose it to be a continuous map. Having these two assumptions, the map f from x to y is indeed an open map. This is easy to see when you look at the definition of the continuity of the inverse map. It simply means when you have an open set on the right hand side, the pre-image on the left hand side is also an open set. Of course, everything looks very similar. Here you see we have the inverse map from y to x. Then we take a subset A in the space X, which is on the right hand side of the inverse map, but on the left hand side in the picture, so don't get confused here. Then we go to the pre-image, which is here again denoted by the power minus 1. Okay, you could think this is an overload for the notation, but indeed it fits together because this is simply the image of A under F. This comes from the one-to-one correspondence we have by our bijective map F. Now with this example you should see that the definition of an open map looks similar to the one of a continuous map, however it's completely different because it goes the other way around. Okay, then let's write down some concrete examples of open maps. Maybe a simple example would be to look at a normal function between the real numbers. Of course, r is just given with the standard metric, which means the absolute value, and I want to send x to x cubed. This has to be an open map because f is bijective and the inverse is continuous. In the same way, we can construct a counterexample. Just look what happens when we send x to x squared. Of course, we can't use the general example here because it's simply not bijective, but still it could be an open map. Of course, this is not the case, it's not an open map, as you can see when considering the open set as the open interval -2 to 2. Then the image is simply the interval 0 to 4. And there you see, this is not an open set in R. Now with your new knowledge what an open map is, we can finally state the open-mapping-theorem. The important ingredient you always should remember here is that we need Banach spaces on the left and the right hand side. So the completeness of the spaces is essential here. Now for a bounded linear operator T, where I use the notation with the curved B again, we have that it is surjective if and only if T is an open map. And that is the famous open mapping theorem. It just tells you that surjectivity for a linear bounded operator between Banach spaces is a strong property, because it implies the openness. Indeed, the implication from right to left is not so surprising and easy to prove. The actual work one has to do from the left to the right hand side. Therefore, the proof of the first implication is a good exercise for you, but for the other one, we need a whole other video. However, before we do that, I want to use the next video to show you an important consequence of the open mapping theorem. It's called the bounded inverse theorem. Hence, please watch the next video because this consequence is very important in a lot of applications. So have a nice day and see you then. Bye!